Krishanshu, please start the proceedings.
Yes, sir. Good day to everyone. My name is Krishanshu Kori, pursuing my MTech in Computer-Aided Structural Engineering at IIT Hyderabad. I feel honored to extend my warm greetings to all who are present here. On behalf of the I-Structured IIT Student Chapter, I want to take this opportunity to welcome us guest speaker, faculty, scholars, the research fraternity, industrial professionals, and all the students to join the online session on the topic Salient Changes in IS 875, Part 3, 2015, compared to its 1987 version with recent research advances in across wind loading of all tall structures. It is my privilege to introduce our guest speaker, Dr. Sasankasekhar Mandal. He is a professor in the Department of Civil Engineering, IIT BHU, Varanasi. He gained extensive professional and academic experience, having served as a design engineer at Development Consultants Limited, Kolkata, assistant surveyor of works in the Military Engineer Services through the IES UPSC, and the lecturer at BITS Pilani. Dr. Mandal is an active member of several BIS communities, including CED 57, SSG 21, and 22. His research focuses on wind effects on structures, advanced concrete technology, and seismic behavior. He obtained his undergraduate degree at civil engineering from Jawadhpur University, Kolkata, and completed his postgraduate and PhD at IIT Roorkee. Dr. Mandal has supervised more than 80 MTech dissertation and 6 PhD theses, covering diverse topics such as wind-induced response of tall buildings, seismic vulnerability assessment, confined masonry behavior, FRP AICTE sponsored, and wind energy engineer potential in coastal cities. He is the author of an AICTE sponsored book on concrete technology, currently being translated into 12 Indian languages. His contributions have been recognized through awards, including the Best Thesis Guidance Award in Wind Energy from ISWE Roorkee and the Best Award from the Indian Concrete Institute. We are truly privileged to have him with us today. Before we start, a small announcement for all the participants. If you have any questions or queries during the session, please type them in the chat box. We'll address them in the Q&A session at the end, moderated by Dr. Praveen Kumar Venkat Rao, faculty advisor of the student chapter. Now, without any further delay, we'll turn the time to our speaker. Sir, over to you.
Okay. So I share my slides.
Sure, sir.
Yes.
Share screen, share. So I have to do entire screen, share entire screen and say.
Yeah, you can do that, sir.
Okay. Is it
Yeah.
being shared? Yeah, it's being shared. And
Yeah,
so,
it is being shared.
could you see the PPT?
Yes, sir, I can see the PPT. If you can
Okay.
open it in a full screen mode. Yes. Perfect.
Okay. So I am happy to be with all of with you all, especially the southern part of my own motherland. And as we know, I used to teach human values for 10 years. Here also it's become a very popular course. About 185 students out of 600 BTech students used to opt for this course, Ethics, Philosophy and Values. I am a student of Ramakrishna Mission, that is from Purulia and Narendrapur. Then I went to Jadavpur University. So my dean and director gave the charge of teaching values, although practicing is more important and difficult also. Especially we must try to imbibe Indian values. So to start with this topic, actually, when we were very young, we were told that Sri Hanumanji used to fly himself because then I asked that Ramayan, the person who is the Kathak, my Tauji, means my not by blood relations, but elder brother, my father used to call. So we used to call Tauji. So I asked him, so there are certain stages of flying. He said that one can fly using say Pavan Putra Hanuman. So wind engineering is related to that little. So in the beginning, we bow down to the deity, you may say, and the steps you can reach that level, and then we can also fly. We know that Adi Shankaracharya ji also, when his mother died, he got the news and I mean, about to die probably. Yeah, before death. So he got the signal from Badrinath or so in the northern Himalayas, and he took those techniques probably by the yoga, some yoga techniques. He flown himself up to his village in Kaladi, somewhere in Kaladi. Yeah. So that's possible. Nothing is impossible if we really go through it. It's possible. Then also when I was in village, then there was a lot of Kalbaishaki. You know, Kalbaishaki is there in the code part 3 itself. It is a very strong storm which come occasionally, particularly in the Bay of Bengal. Also, my IIIT Hyderabad, our IIIT is located in a zone, although it's a bit inland. However, we have a lot of cyclones which damages our Andhra Pradesh. Probably Andhi, well, the word has given to the word Andhra Pradesh and so on. So let us go through. So first code, this code was firstly developed even before 1964. That year is about 52 or 56. So firstly in 1964 also you will see only few pages. All 875 were combined there. Part 1, part 2, up to part 5. All were combined in the same version of very few pages. I have that version also. And then in 87, it was developed based on the research of that 34 years, 33 years, 64, so 23 years, okay, and 24 years about that. Then again, when another we have another 28 years we took. In 2015-16, we had the new code. Before that, in 2004 or 2002, in a conference of National Engineering Conference, Professor Prem Krishna of IIT Roorkee, it was held in 2002 at there only, yes. So he gave the first version of that modified draft, which was further modified by a project funded by Gujarat State Disaster Management Authority to IIT Kanpur, and IIT Kanpur gave the fund to IIT Roorkee. Four of my professors, Professor Prem Krishna, Professor Krishan Kumar, and Professor N.M. Bhandari, three of them did the best work for this new code. Although many researchers are there at the background, like RWDI, current Suresh Kumar ji, and many, and even Indian wind tunnel experts also in Roorkee, in Kanpur, later on. Now the latest wind tunnel is in JP Guna, and so on. So we are growing, the country as a whole, we are growing in this area, and we are getting the new results, and we are trying to codify the same. So this lecture will be on that what are the changes in the new code till 2015, say, and we are moving on further, in fact. So before giving further time, there are three major approaches of approaches to wind engineering problems. Right. So can I hide some of the things? This meeting is being recorded, okay? And yeah, so that much is, yeah, it's there now. Okay, so this one, can I hide? Yeah, done. Okay. So there are these three major approaches are like statistical wind engineering, which is using the data obtained like the Davenport. He first published 1964 in this time. This paper were originally collected from IIT Kharagpur journals. And they were actually dealing with gas factor method, which you see in clause 8 and 9 nowadays. Then those statistical data is actually obtained in boundary layer wind tunnel experiment. So experimental wind tunnel engineering now. And you will be happy to know that our ACRC Chennai, then CBRI Roorkee, even our institute is having a small wind tunnel. And apart from that, full-scale model testing also has been done, like Florida International University, Texas Tech University, where our own Indian PC Mehta sir was there, who led this engineering further. So boundary layer internal experiments as well as full-scale experiments on site, in ambient atmosphere. Then the third one is now emerging, which are supporting each other, complementary to each other. That is computational wind engineering. I did my PhD on it, which is an extension of using this technology. This one, so CFD, it's an extension of Reynolds average Navier-Stokes equations, also known as RANS equations, and so combined with some turbulence kinetic energy or turbulence models. So if you go to ANSYS Fluent 3D, now they have large eddy simulation, K epsilon model, K omega model, and vorticity omega phi model. So many methods are there, computerized now. You can give input and get the output. Of course, be careful about the boundary conditions. So our contribution was on these boundary conditions during my PhD. So many people, I'll show you one computational domain. Okay, that is far beyond the slides. Let us go back. So my paper, probably I'll tell you at the end. Let us go through. But just quickly, what happened, if we take RNS equations, then if you do for 2D only, then first we have to take one equation which is called conservation of mass equation or mass conservation equation. And then you have two equations, x momentum and say y momentum. Normally we call say 2D one, y is vertical here. And then turbulence kinetic energy equation and turbulence kinetic dissipation of turbulence kinetic energy equations. So in 2D, we have to solve all these 5 equations simultaneously, where it is very difficult. All are nonlinear, all are using eddy viscosity, which is a damping factor, basically, like in structures. It is very small and no convergence can be achieved. In the long run, we could find one paper of Arausian Ferris from Australia, and we get some data from Oxford University by Minson et al. And using those data and using control volume method and so many approaches, we could make 5 chapters. And finally, main contribution was in the boundary conditions. So we found out the errors from all these 5 equations and integrated them along the boundary. And we got what we got. We got a residual error index. Then we minimize those 5 errors. It's a huge mathematical task. So while present, I must give this. I must pay my ovations to my teachers, Guruji. Both of them were from Roorkee only. So we could go give that paper to the world. ASC in the beginning. And we compared with experimental data also, 10 experimental data right from IIT Kanpur to Oxford University and other universities of the world. And we proved that our equation and our approach was correct to define the boundary conditions. And without boundary conditions, we cannot solve proper exact boundary conditions. We cannot solve any equation. However, whatever with expertise, then even there is one more I should say, you must read one paper, H.L. Stone, 1964. Okay, again, 1964. So that paper gives out how to solve these equations implicitly. Very fast it will solve. Then we got a new light that this could be a PhD now. Then we solved those equations and got some good results and published in American Society of Civil Engineering Journal of Hydraulic Engineering. Again, there, Professor Rodi from Germany. Just I'll conclude this. This becoming long, it seems. So Professor Rodi was associate editor, and editor told that this is no work, it cannot be published. But late Professor Rodi told, no, I see something new in the research. So then finally, after 3.5 years, we could publish that paper, which is a landmark probably, because many people used to say we have taken this boundary condition, the other one, but nobody used to prove that this is correct and how to prove that this boundary condition is correct. So we gave a methodology in computational wind engineering. After this, now go to the major points. So you could see this is a full-scale testing facility at TTU, Texas Tech University. And also we have similar, as I told, in CBRR and ACRC, Chennai. Then boundary layer wind tunnel can be open-ended like this. In one end, we have a fan And the other way it exits the air. Otherwise, we could have a closed circuit boundary wind tunnel where the whole air will be flowing in a closed duct, 4 ducts, you may say, like a rectangle. So as I told that Arousey Ferry's 1987 paper that helped us. So we simulated, we took these 2 buildings and 3 building model and simulated those, got some good results and published in Chennai. So now go to the code really, probably. Let us see. Otherwise, yeah. Okay. So first, you should see that in our code, we are providing basic wind speed, design wind speed. So this wind speed comes from different scales and their effects. Like you see, Beaufort scale, Saffir-Simpson hurricane scale, Fujita tornado scale. So we get some different types of scales and different types of wind speeds. Basic wind speed has a special definition that it is taken at 10 meter height and so on, right? Based on the category effect. So again, wind-induced disaster in that report I told in the beginning, that's the report of IIT Kanpur funded by Gujarat State Disaster Management Authority. And these are the casualties in wind, losses of loss events like this. I go to these changes now. So here you will see aerodynamic roughness heights for individual terrain categories have been explicitly included and are used to derive turbulence intensity and mean hourly wind speed profiles. So we have got explicit equations now, almost. Earlier it was only data. Aerodynamic roughness we can now calculate. The previous classification of structures into B and C classes has been deleted. Only A class or only single class has been provided in the new code. Earlier code we had 3 classes, A, B, C, and those have been deleted. And K2 also there are two tables. Yeah. So there are 2 tables in the beginning for peak wind approach and later on for mean wind approach. So now K2 factor has been combined to only 1 table, and that is the only table now for K2. Earlier code has 2 K2, okay, tables for K2. One for peak wind approach where we take the averaging time for 3 seconds. 3 seconds averaging. The other one was the hourly mean wind speed. So that is also known as mean wind approach, which is also a part of gust effect method or gust effective factor method. So these 2 one table has been deleted now. And additional modification factors like importance factors has been included in the terms of cyclonic factor, cyclonic modification factor for coastal areas up to 80 km from the boundary of the coastal boundary of the country. Okay. Then also we have now simple, okay. Simple empirical expressions have been suggested for height variations of hourly mean wind speed and also turbulence intensity. While doing PhD, when we had the last code, we didn't have any equation for turbulence intensity, which is very important. Now these equations have been given in the new code. Also directionality effect, area averaging effect, like area averaging effect, directionality effect, it takes care for the direction of the wind. What is area averaging factor? Suppose we were doing thesis in local pressure coefficients and global pressure coefficients. So if we take a pressure value which is for a small building, then it will be a bit high when the same pressure value is applied for a very large wide building that whose base dimensions are very large, say 30 meter by 35 meter. Normal building ka to it's lower in normal buildings, but suppose we are designing a building for which is having 35 meter one face. So in that case, if we take that higher value of wind pressure, we will be on uneconomical and unsafe side. So we now have got some factor like area averaging factor depending upon the area of the frontal face, where say wind is considered as acting normal to that face. So accordingly, we have got that also, and guidelines to account for wind-induced interference for tall buildings or small buildings have been included in this new code. This is important. Now, interference factor, because of heavy urbanization, we have one tower, we have the next tower and the third tower, and so many towers at one place probably. So it has been, if you see the book of Simu and Scanlon, that is the one of the good book, E. Simu and Scanlon, can read further for interference effects. And now we have got a lot of papers. Like first paper was given by B.C. Khanduri et al. State-of-the-art interference factor, interference effects have been given there. That is very old, 1999 paper. Then we published in 2013 also, and many people are publishing. However, it should be taken care, and the new code has given some guidelines towards that. Okay. Any questions so far? I could not see you, anyone, but if you have question, please let me know, right? Am I audible now? Audible, everybody?
Sir, you are audible. We will take the questions at the end, sir.
Okay, fine.
Thank you.
Okay. So detailed boundary layer wind tunnel tests have been also recommended, that to find out actual interference factor. Suppose when we presented the same thing, there is a paper of Zai and Gu, a very methodical or stepwise he has explained and done CFD analysis, keeping 3 buildings, 2 buildings, and then he recommended that this interference factor may be as high as 2 or 2 point more than 2. So then my seniors told this cannot be. Then first time, the first MTech thesis when we presented here, then we could learn more here. So then gust factor method has been now included for across wind response. Earlier, already the along wind response equations or graphs were there. Earlier graphs for along wind response calculations were given for the parameters such as background factor, energy ratio, and length scale turbulence. But presently, the present code also gives across wind response of tall buildings, some calculation, some idea, which is again new. Okay, so what are the different codes that has been taken care during the new code? They are BS code 1991, 2005, as they say, but they are all now these codes also have been revised, some of them. So we have to keep pace with all this. So this last one is Japanese code. Okay. Now let us see some of these parameters. So first parameter is aerodynamic roughness heights for terrain category. So aerodynamic roughness height is now given like this, very easy to remember. For category 1, where there is very small buildings of less than 10 meter, less than equal to 10 meter, it is 0.002, and the values increases 10 or the order of 10 times. Simple empirical expressions have been also suggested for variation of hourly mean wind speed and turbulence index. This is repeated. And as an approximation, the roughness length is approximately 1/10 of the height of the surface roughness elements. Okay, then if you see, how do we calculate this definition of aerodynamic roughness? So there are certain, this is a parameter, is a parameter of some vertical wind profile equations that model the horizontal mean wind speed near ground. In the log wind profile, it is equivalent to the height at which the wind speed theoretically becomes 0 in the absence of wind slowing obstacles. So roughness length is taking care of the where theoretically it is defined like this. Okay, it is so named because it is typically related to the height of terrain roughness elements, that is protrusions from and or depressions into the surface. Okay, so this type of I got it from somewhere. So these are the equations, turbulence intensity equations given in the code. Earlier it was not there, now we have. Similarly, K2I has been expressed in terms of this type of equations. Okay, so K2 is renamed as terrain roughness and height factor. The previous code termed this factor as terrain height and structure size factor. Okay, now what is category 1? Where, so okay, I told category 1 as 10 meter, but category 1 is where obstruction is 1.5, and category 2 where obstruction height is 1.5 to 10 meter. Category 3 up to 10 meters with some isolated tall structures, and category 4 where city like central business districts where height of structure is above 25 meter and having industrial complexes like tall buildings, you may say. Now, category definition, the new code says like this. So you can go through the codes and see this. I am moving with ahead with this. Now, earlier code, we had A, B, C. Now the present code has only A, or it's not mentioning whether A or not. But these values are close to, if you see the last line, close to A. That's why I was telling A. Or in the beginning of the code, it's written that class A is written, others have been deleted. Okay. So K2 is the major modification here. And if you compare these values, you can largely very slight difference. Instead of 1.4, now it is 1.35. So K2 values have been just reduced marginally. Now table 33 provided in earlier code was like this. Again, you see, which has been deleted now because of refinement in the provisions in the this mean wind approach. So that we'll see later.
मीटिंग करा था तो
Online.
उसको देखेंगे
शाम को रहेंगे
हाँ शाम को तो रहने
हमको देखते 6 बजे 6:30 बजे डायरेक्टर के साथ मीटिंग है 5:30 बजे
ठीक है
उसके बाद देखते हैं नहीं तो करते हैं
बैठ के सर उसको खत्म किया जाए देखिए
रहेंगे तो करते
ठीक
हैं Importance factor K4 importance factor K4 an additional modification factor K4 that I told that to take care of cyclonic regions. So now one thing is clear. Suppose the factor K4 is maximum value is 1.3. So if we take design wind speed is equal to K1, K2, K3, K4, multiply these factors into VB. In that case, 1.3 times the basic wind speed will increase. The pressure will increase by pressure is equal to 0.6 Vz square. So it will increase by 1.3 square times. So it becomes 1.69. So the wind load becomes very high. So we got many queries come sometimes like those who design multi-story buildings. Although I am not in this committee, CD, this there is civil engineering division, BIS committee. I am in CD 57, but this committee is a different one. Okay. So K4 is to be taken as given by this code. Then in between, in the meeting of cyclone, I am in the committee of cyclone registered shelters, CED 57 of BIS. So we had a discussion. Some people said that your K4 value is too high, 1.3. So then we got a project and saw and refined this value through another code. So if you are interested or while designing such buildings in cyclonic region, kindly go through the codes published by CED 57. In one code, we have dealt with this K4. Okay, we have published 5-6 codes. In one code, it is there. Okay, so now let's see. I was telling it's 1.3. So it's when we do square of it, 0.6 Vz square. Oh, this is the code 15498. So kindly go through this code for further reading. Okay. So this code was basically developed by that project done by IIT BHU, Professor Arnab Sarkar, and I was also in that team. Through a PhD, we did it. Huh? So now, let's see. So K4, how to define 80 kilometer, 60 kilometer. Okay, cyclonic storms generally extend up to about 60 kilometer inland. So there, or the earlier one, if you see, they are also 60 kilometer. I told 80 kilometer. Normally, we should go up to 80 kilometer. And one thing I'll tell you, I have seen being a student from the village, when our Andhra coast is hit by any cyclone, Varanasi feels it within 1.5 day, maybe 2 nights max. Okay, so that wind speed is about like that only. You will that can be interesting to observe. I follow the Indian meteorological data and forecasting through All India Radio. Whenever there is any cyclone or any such event, I try to see when it is coming to Varanasi after hitting the east coast of India, my country, of my motherland. Okay, So it's interesting to see all those, how much does it travel? How much does it take to travel? Okay, how many hours? So it's about 24 to 36 hours it takes to travel from your Andhra coast to Varanasi, because there are so many mountains also. Okay, so next, wind directionality factor, considering the randomness in the directionality of wind, and recognizing the fact that pressure or force coefficients are determined for specific wind directions. It is specified that for buildings, solid signs, open signs, and so on, a factor of 0.9 may be used on the design wind pressure. As I told, because it is very random, so at a time, for a sustained period of time, this force cannot be constant. So we reduce it by this factor, wind directionality factor we call. Similarly, area averaging factor, as I told in the beginning, if your area is 10 meters square, it is 1. But if the area increases, then force will be equal to area multiplied the design pressure. So if you multiply that much of area, it becomes huge force. So we must reduce by some 10% or 20%. So linear interpolation for intermediate values are permitted. Is it okay? So this is known as area averaging factor. Tributary area. So this is for local pressure and global pressure, overall structure and individual elements. So one thesis we could do with Dart fellow on local pressures. One of my students went to as a Dart fellow there. He did on these local balconies. In balcony, suppose a building, multi-story building is having balcony all over its height. Then what will the change in the design wind pressure? So that has been done experimentally as well as statistically. So wind-induced interference, this is more interesting because earlier course didn't provide for it. And this can be done using CFD also, as I told, Zai and Give, and so many paper, BC Khanduri paper. Many people have done using CFD, I mean CWE, now we call computational wind engineering. Computational wind engineering. So interference factors, same thing is written here. You can do by wind tunnel test or CFD studies or both. It will be better to do by both. Okay. And then to account for the effect of interference, a wind interference factor has been introduced as a multiplying factor. Now, if you see the literature, there is this factor can be of different types again. Sometimes we call it mean interference factor. Sometimes we call envelope interference factor. So, and so on. Envelope means the higher one we take. Mean, we average one we take. And so on. Huh? And then, since the values of interference can vary considerably, so based on building geometry and location, the given values of IF are a kind of median values and meant only for preliminary design estimates. Otherwise, you have to go for specialist literature or wind tunnel study as told earlier. So these are some values. Go to the figure. This is the different zones and this is the figure. So you see, we have a we have a building here of dimension B by 4B. So this building is the constructed in the beginning, we assume. Now our new building may be located at zone 1 on the downstream side, upstream side, or it may be on zone 2 or zone 3 or zone 4. So for all these 4 zones, we have been given 4 coefficients. Again, you see interference factor, if you take, it is again becoming 1.69 times the design wind speed. Design wind pressure. Design wind pressure will be 1.69 times. So probably you are getting an uneconomical building. 1.69 multiplied by 1.69, because if it is in the cyclonic zone, we will multiply twice this thing. So about 3 times the load is coming. 1.69 means 1.7. So 1.7 multiplied by 1.7 is 2.89. So about 3 times the load is coming. So one of my classmates, even he's a designer in Mumbai region. So his building was becoming 3 times, his wind load becoming too much. So he asked what to do and how to optimize. Otherwise, becoming in the beginning of when this code came in 2015-16, around that time, many questions used to come. So we have to go to specialist literatures like Simu Scanlon, latest research paper, and accordingly we have to optimize or bring down suitably or go for internal studies and prove that this is not 3 times. This is lesser, about 1.5 times overall increase in wind speed. So accordingly, we have to do lot of literature, consulting literature, existing literature, or go for wind tunnel studies. Yeah. Okay, so on, right? So we get some glimpse that now this factor is to be taken care of. X is the distance between the new building and old building, and according to the positioning of the new building, say zone 4 on the downstream side or zone 4 in the upstream side. So could you see see the distances carefully. Upstream side is zone 4 is very far away from the existing building, whereas it is very close here. So very interesting is to do some further studies, which we did through 3-4 MTech thesis. Okay, so now the effect has been taken like we did. I showed you in the beginning one model. So ANSYS modeling we did through this MTech thesis, and this is the finite element discretization. I mean, domain discretization, not finite element. It may be meshing. It's ANSYS means we are using finite element only. So then we did isolated building flow around the isolated building and so on. So we placed the other building at the downstream or upstream. Okay, it's about 10 years back we did study. Anyway, we could see that now the pressure contours have changed to some extent, not that drastically. Similarly, if we have 3 buildings and so on, so these are quite interesting nowadays. Many experts are there in India. First time when I studied started my computational engineering problem, I could see only IIT Kharagpur and IIT Chennai doing this type of research. Professor Aparasamy and Ghosh, Professor Ghosh of Aerospace Engineering, did this type of CFD and experimentation. But now we have so many experts in India, really happy to note. And mean drag interference factor was found out, and these are the ANSYS one. This is Khanduri et al. I told. No? So could you see? ANSYS is giving bit higher values than that of predicted by Khanduri et al. Okay, so that's what Giant Gu, probably his name is there or not, I'll see quickly. Not there, okay. He also showed some for certain locating 2 new buildings around a square building, the value was coming 2 times, more than 2 times. So my seniors told it's not possible. That was in around this 2015 and before that. But it is possible. So we have to be very careful when especially we are going for multi-storied buildings. Interference factor should be taken carefully. So these are the simulations done by us using ANSYS, one of the MTech thesis. Again, so our values, the Khanduri et al. Values are becoming more when the SIV value means our values are lesser and higher. At certain place, it is crossing each other. Anyway, so go forward again. This is a simulation. Then these are the conclusions from that paper. Now, changes in the along wind response. This is very major nowadays. You know, the earlier code, very easy to remember is earlier code give us lot of graphs, but now the present age is, so we have to read the values from those graphs. I'll show you. But the present code gives us numerical, empirical expressions. Empirical expressions now could be easily programmed and you can find out the actual value from those equations, not to read the graphs, which cannot be so easily discretized or values has to done manually. And so now the designers can use those formula easily. So what is the Gast factor? Gast factor is the factor method is for evaluating along wind response or across wind response also. So Gast factor, the earlier code, this expression was given 1 plus GF into smaller roughness coefficient. This GF is peak factor and B is background factor into 1 plus phi square and AC by beta. So first part B, this is known as background equivalent static wind load factor. It is also known as background factor or background equivalent static wind load, ESWL. Along wind response or across wind response are also known as equivalent static wind load. But actually, dynamic responses, aeroelastic and aerodynamic responses have been statistically and carefully has been statistically processed, and these equations were given by firstly by Davenport in that 1964 paper. On between 1967, he has 3 papers. He gave this formula for the first time, where S and E and beta, let us see that these are the energy content, beta is the damping factor, S is, and so on. So S is size reduction factor. So for all these factors, we had a corresponding figure. Like for B, we have figure 9. For S, figure 10. For E, energy content, measure of available energy in the wind stream at the natural frequency of the structure. It's very interesting now. How do we model this energy at natural frequency of the structure? So this has been done for the first time by Davenport, who is also known as father of wind engineering worldwide. So beta, so I have got a book on his life. So he like Zinkevich guided so many MTech thesis, PhD thesis in finite element method. In his book, it is mentioned. Similarly, Davenport was a very simple professor who used to just behave like a student throughout his life till retirement or even after retirement. So because of that, they did a lot of research with the students. He did, and he could give so many formula. Huh? So in Canada, somewhere in Canada. Okay, so GFR in root over B by 4 is the phi expression. And so actually here, one thing I was going to tell that this part is nothing but it's a sort of SRSS method has been taken. Background, square root of background factor, and square of background factor and square of resonant response factor. SE by beta, it is also known as RESWL. What does it mean? Resonant equivalent static wind load factor. So then square root. So square root of squares have been taken, and like that is as a model. Okay. So see the new code. This is the new codal expression. Now it has been changed like this. Some more factors have come in. GF, which was outside, you see GF is nothing but peak factor, which is now defined in terms of background component, and it's different. You see GV and GR. This is background component and this is resonant component. So accordingly, background component means wind environmental scenario, that is velocity fluctuations, randomness in wind. How does that is taken care of? That peak factor is known as GV, whereas GR is the, you see, peak factor for resonant responses. So we have now so many expressions given. Earlier all were in figure form. Now see, okay, so there are so many now. How the second order turbulence intensity affects the these expressions can be done research, apply this research on those expressions. LH, earlier we used to find graphs, now we use these expressions. Okay, see the graphs now. LH, see, earlier we used to, this is turbulent length scale. A measure of turbulent length scale means you know, the wind is, if you already have, you frequently see that storms, there is eddies, there is small eddies and bigger eddies. So these bigger eddies and smaller eddies, they have certain turbulence length scale. Like you see terrain category 1, because there is no obstruction or minimum obstruction like sea coast, a very small isolated structure, only shrubs actually, category 1 में building in a 1.5 meter height. So plants and trees are there. So there the turbulent length scale will be very large, possibility of getting LH higher. Whereas in cities, it is quite low because that turbulence cannot be generated amongst too many buildings, isn't it? So LH is lesser, like that you can understand physically, right? Similarly, roughness factor is more in terrain category 4, like central business district, where we have so many tall buildings. Okay, and lowest in category 1. Is it correct? See the figure. Then background factor is now also we have these expressions. Just go through those coder with view only. On net also you can find. So now this background factor, earlier this graph was there, but present code gives us these expressions. So do they match? Would you really get those curves using this one? This can be a study again. And what is the error? This I was thinking while preparing these slides. What could be the error between those graph and these expressions? Data from this expression versus this data. Is there any error and how that affect the designer? This could be a good topic for PhD even. Okay. So then we have CY, CZ, lateral correlation constant, CY and CZ. We take 10, this we take 12, but what are they? Lateral correlation constant, do you remember that Reynolds stresses? You dash suppose wind velocity has a component, mean component, and also we have a component which is the fluctuating component. So because of fluctuations in U dash direction and the other direction, so there will be some correlation. So if we take UV, U dash, small UV, I mean, U dash V dash, then take average it. So we get its Reynolds trace, we call, multiplied by rho. We got Reynolds traces. Okay. So those, that means lateral correlation amongst these three axes, or two horizontal axes and one vertical axis. So that is taken care by this CY and CZ. I hope I could little bit explain. And size reduction factor. Now we have got the expression like this. Earlier we had a graph like this. Okay. So one thing is that if the reduced frequency, which is the non-dimensional frequency, could you see F naught into H is velocity. F naught is a frequency multiplied by meter. So we got meter per second divided by VH, which is the velocity at the top of the building or structure. So we get a reduced frequency or dimensionless frequency, which is in the x-axis. And based on that, we will get a size reduction factor. So what is this physically? Can you get? You give some time, small thinking and I mean little bit thinking and studies is required. So it depends on lambda as well as reduced frequency, size reduction factor. But it is actually, it takes care of the structure size. Okay. And then E, energy spectrum of turbulence in the energy content in the turbulence of wind stream, given by this expression. Again, you see N is a effective reduced frequency, and using this expression we can find out E, or the earlier code used to give this. Okay, so as the frequency that is increasing, the energy decreases like that. But it's not just not frequency, it's a reduced frequency or effective reduced frequency. So now the new code also has given across-wind response. So a method for computing across-wind response of tall buildings. The acceleration also has been given in our code. Earlier, these were firstly proposed by GU and Q1. Then we did some MTech thesis. These are the references, Patidar and papers also. Patidar and this thing. We did three, four. No one PhD also an across-wind response. What we have seen that if normally the tall buildings dynamic effect is to be taken care of when the total height of the building divided by any of the smaller dimension is more than 5. So what we have seen that if this H by ratio A, this ratio also known as aspect ratio, if it increases beyond 8, so the wind load, across wind load may be more than along wind load and drastically very high. Also, in 2007, it was noted during the Jinmao building investigation or before construction of such tall buildings like Jinmao building, there is a paper. Number of papers are there on that. It has been noted that square buildings are subjected to higher across wind loading. So to remember, always remember that in IS 4326 or IS 1893, we talk of circular sections or square sections are best. Circular is the best, but square sections will behave squarely for earthquake forces. Squarely ones will very strongly. Like when my English teacher told that behave squarely, or a square drive, cricket maybe bolte square drive, we have given a square drive, means very strong drive, outbound, out of the boundary it goes. So squarely, we means if a building is square on plan, it will get least seismic force. It is known in 4326 also, it is written. Whereas across wind loads will be higher if we go for a square plan building. It has a lot of research and MTech thesis, PhD thesis have been done on it, and it has been really seen that square buildings are more susceptible to across wind loading, which may be more than along wind loading. But how is it generated for us? So is there any figure here? Okay, just quickly I'll. Okay. So that basic figure is not given. So I just take the help of this figure. Okay, this figure. Suppose the wind direction is such that, suppose, could you see this figure? Wind direction is perpendicular to B. Okay, so it is expected that the building will vibrate in the direction of the wind, and that wind load is known as along wind load. Whereas due to vortex shading, and we do that through Strahl number given in the code, the expression Strahl number, or Strouhal number, Strouhal, HL, the Strouhal number. So we can take care of this vortex shading. Because of random vortex shading, that vortices will streamline separation will occur at this corner and the other corner, and it will hit the building itself. If the building this side is large, it will hit the building itself. So the building will now vibrate in the perpendicular direction of the wind. Similarly, on the other side also, if they get separated, and this become a very random phenomenon, and at certain velocity of wind, this building will start vibrating in the across wind direction. So that is known as across wind response, and it is very critical for square sections. That's why our code has given, you see, V by D 1:1. As I was telling, square buildings are subjected to higher across wind response. So now see, these are the expressions. The base bending moment, that is bending moment at the base of the tall building, MC, can be estimated using this formula, where again GH is a peak factor, PH is the design wind pressure. See, hourly mean wind pressure is equal to 0.6 Vz square. Why it is 0.6? The reason is half into rho v square. Per unit energy or pressure is equal to energy per unit volume. So mass per unit volume is pressure, density of wind, and density of wind value is 1.2. So half times 1.2 is 0.6. That's why PZ is written as 0.6 Vz square. Okay, so 0.6 Vz square is pH now. And V is the breadth of the structure, H is the height of the structure, K is the mode shape power exponent for representation of the fundamental mode shape, as represented by psi z, z by h to the power k. And so here we have to do a little bit of study on this mode exponent factor. In 2007, first time it was noted by the researchers that this can play a bigger role, and we can get high base bending moment due to across wind. So MC, the design moment, MC, bending moment, peak base bending moment, design due to across wind load can be found out by this expression, where K, FC is there somewhere. Okay, K, how to calculate K? A mode set, this one is fast mode and so on. Then C, we have used this FZ, the distribution of loads can be found out by putting MC here and so on. And FZC is the across wind load per unit height at height Z. So now we get a different expression for across wind loading also. And this expression is given in peak acceleration. Normally, the inhabitants of the building or users of the building should not feel very high acceleration, or it should not be beyond their tolerance limit. So what do? We must calculate theoretically or ensure that the probable acceleration after construction is within the permissible limit. If you see 16700, Indian standard number 16700 tall buildings, there you will see that certain permissible values for acceleration has been limited. And this permissible value is more in case of commercial buildings. Means residential buildings should not be subjected to certain values which are lesser than commercial buildings. Okay, so we can check using this formula whether our pressure value is increasing, acceleration is increasing than the permissible limit or not. So with this K value for different types of structures, K value has been given here. Slender frame structure, moment resisting K is equal to 0.5. Again, can we justify why it is more in case of lattice tower, why it is 2.3, why it is 1.5 here, uniform cantilever, slender frame structure, moment resisting, it is 0.5 now reduced. So we have to go into the detail of this formulation and find out why these values are changing. And these are the graphs again from the new code. These graphs were prescribed, has been prescribed in the new code itself. So go through it carefully. So again, you see on the x-axis, we have a dimensionless factor. So whenever you do any good research or any new study, try to publish the results in the dimensionless form. This parameter should be dimensionless form, dimensionless. Then you can get more information which is hidden. So crosswind for CFS, we were seeing in the last few slides. CFS variation has been given, or you can take from here. This is a coefficient, crosswind force spectrum coefficient, which is taken to find out the crosswind loading. Okay, and you could see at certain velocity, at certain reduced velocity, we call it ratio 6 to 7, between 6 and 7, it is the highest. Okay. So what we call that at certain reduced wind speed, negative aerodynamic damping may occur. That means at very low speed, even at certain very low speed, when we get the value of the based on the first mode and B, we can get their value say 6 or 7, then we will get very high cross winds force spectrum. So this has been described by the experts as negative aerodynamic damping. At certain reduced velocity, we'll see that negative aerodynamic damping occurs. The building starts vibrating of its own, and it may lead to failure. It has been seen that in certain cases, like probably Tacoma Narrowby Bridge, that which failed due to crosswind or buffeting response, all those things are also linked to this discussion, which I was telling, negative aerodynamic damping. See, lot of research are being done now in this area. And say again, you could see there are two pictures, one for 2:1 and 1:2. Again, around 8, you see we are getting peaks. So we have to avoid these peaks. Accordingly, we have to keep the dimensions of the building, stiffness of the building. Where is the stiffness factor taken into account? Into F0, isn't it? F0 is the fundamental or first mode of vibration frequency. Yeah. So it is taken, the structural parameters, stiffness factor has been taken into consideration by F0. So if it is stiffer, and velocity may be high, then this ratio will be lesser. So it also depends on the other dimension, B. B is the smaller dimension. Could you see? Here it is smaller, of course. But for this one, it is the higher one. So one dimension is taken either of the B or D. Here it is taken B. B is now defined in terms of the wind direction. Okay. So when the wind is hitting the smaller side, so we have to take that only, B. If it is longer side, then we have to take this B, 2B. I mean, twice the other dimension. So B only, it depends on B. In terms of B, it has been prescribed. So now, to ascertain which code is more conservative, comparison of along wind responses has been done in some of the theses. So we took these 7 configurations. We took actually 12 meter by 12 meter is the square building, but we varied the dimensions based on the wind direction. we kept 12 meter, 12 meter, 12 meter. Then we kept the other dimension 12 meter, and these three figures were plan buildings were taken, and all calculations were done in Excel and MATLAB, and we found this type of along wind force in 2015 is more than 1987. Of course, we must tell whether it was taken cyclonic region factor or not, or that other factor 1 point. So normally 2015 is more conservative. It has been seen now. It depends on different parameters, of course. And you see 2015 is giving higher load than 87. And these are the references for comparative study on gas factor. And comparative study using the two codes. Now, these are the some of the other references we went through, and some comparative statements are there, like the Kawale and Joshi calculated wind loads for a G plus 17-story building. Their conclusions show that gas factor has been increased in this 2015, as I told. Similar to that, then value of gas pressure has been increased. There is also considerable amount of increase in bending moment for models, which is designed according to new IS code. The maximum deflection in the topmost story is 57 millimeter for structure, which is designed as per old code, and the new code gives 192. So these are the things. So our new code is more conservative, probably. So it depends. Mostly, it's in general it is conservative. You can conclude based on our study also. So now see, crosswind load is lesser because height ratio is 4. Height ratio means height aspect ratio, total height of the building divided by the smaller dimension of the building. Now, if you go to 7 height aspect ratio, then across wind is taking over or becoming more than along wind, as shown in this graph. And this is just part of a PhD study. Then for 8, it is higher right from the beginning and very high. It is around 750 or 800, but it is 1600, double than the along wind load because of slenderness. So these are the references. As I told, this reference third, you see, the Professor Bhandari, Prem Krishna Sir, Krishan Kumar, and Abhay Gupta. They made the explanatory handbook of the proposed in 2002. This code was given in the conference. This proposed version. Later on, it became the code. Actually, it became the code with some modification. And these are the references of APCW, Asia Pacific Conference on Wind Engineering. In wind engineering, we have every year there is a conference. One national conference followed by an international conference like APCWV or ICWV, International Conference on Wind Engineering. Then again NCWV. So every 2 years, we earlier had a NCWV. Now we are picking up. Last one is in Nagpur this last year, November. And these are this is the paper I was telling, that aspects of inlet boundary condition. If you are interested, can find out this paper, that how those 5 equations, one is mass conservation equation, second and third is momentum equations, fourth and fifth are turbulence kinetic equation, turbulence kinetic energy equations. All 5 were given all those experimental data throughout the world. 10 data sets were very usable. So those were put in the equation. Then all derivatives were calculated using finite difference method and so on. Then those equations, we saw what is the error from each equation, and those errors along the vertical we integrated. So we got residual error index, and then we correlated that with the simulation results also. So just a minute. हाँ सर 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 बोलिए आ गए. हाँ 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 हाँ. ना ट्रिपल आईटी में एक ऑनलाइन लेक्चर हो रहा है 10 मिनट मैंने 4:45 तक. हाँ हाँ अच्छा सर. हाँ सर अच्छा सर जी हाँ उनका भी था सर उनका भी तीनों को मैं मिलके बोल देता हूँ हाँ? सर आप फोन करके सर आप फोन करके हाँ ओ अच्छा अच्छा ठीक हाँ ओ ठीक है ठीक ठीक है ओके अच्छा अच्छा उनका भी नहीं आया अच्छा ओ okay okay sorry for the meeting call from the dean sir so these are the things sir it's very difficult to really do phd in computational engineering which I took about 5 years, being very sincere even then. But it was a really learning experience, and you would be happy to know last sentence because time is going. Like Patankar, there is a book of S.B. Patankar and Charles Hitch. Patankar is an Indian, but he was a professor there in of thermodynamics and mechanical engineering somewhere. Anyways, so he told, go to that book if you are interested in numerical simulation. He told in the beginning of the book, nothing is impossible to model numerically. However, we could do a little bit of that. Then these are the references. So okay. So now question answer session, please, Doctor. Mhm.
Yes, sir. Thank you so much for a very comprehensive overview about this wind loading analysis, which is
Uh,
really critical for the tall structures.
uh,
I now request Krishanshu to please take the proceedings. Yeah,
if required, we'll share further. Let us see each other.
sure, sir. Yeah, Krishanshu, please.
Thank you, sir, for the insightful session. Salient changes in IS 875 Part 3 2015 compared to its 1987 version with recent research advances. In this code, the newer code 2015 one, the improved gust factor, clarified importance factors, and introduced the size reduction factor. It included drag and interferences effects and background response factors. The revised wind speed map dynamic provisions can lead to increased wind loads on certain tall buildings and compared to the 1987 code. And overall, how the newer code is more conservative, as you said. Now, we'll take the questions from the participants.
Okay, thank you, Krishanshu. Sir, we have few questions. If you allow, then I'll read one by one so that we can discuss. The first
Yes.
question is asked by Mr. Sridhar. He's saying the K2 factor is renamed as terrain roughness and height factor. Does it mean size of the structure is no longer considered separately?
It is inbuilt in the roughness factor.
Okay.
It has been taken through roughness factor. You see the expressions given, this K2 has been multiplied by some expression, given some expression in the code. So there the roughness factor has been taken care.
Okay. Okay. Thank you, sir. Mr. Raghupati is asking, do we need to consider K4 factor for entire East Coast for a building which is lies up to 60 kilometers?
Yes. Not only East Coast, West Coast also. Our West Coast, like Gujarat, is frequently experiencing cyclones and due to the disturbances in the Arabian Sea. So in the West Coast also, this factor is to be taken. In the both East West Coast.
Okay, sir. Okay. So the next question from the same participant, when SP64 for revised IS 875 will be get published?
That is a big job actually. Professor P. Hari Krishna, Dr. P. Hari Krishna, CSR Chennai, SCRC. He is the
SARC.
He is the chairman of that committee, of this code committee. So we could discuss about it on this Nagpur conference, and I requested it will take time. If someone has to take lead, I can take the lead, but the chairman has to give the duty that to someone or group of some people who can solve those problems. Say, there are so many problems are solved in that book, SP64. As you have seen, SP64 is number of high-rise buildings have also been solved, and so at least those problems has to be resolved based on the new code. It's a huge, not that huge, but someone has to lead a team as a team. Professor Dr. Abhay Gupta was doing this, trying this, but he could not complete probably. Okay, so Abhay Gupta is a PhD from Roorkee. I
Yes.
can give his email ID also. You can talk. He's good. He's an expert, really.
Okay.
Really expert on wind engineering.
Okay. Thank you, sir. The next question is for facade design. Can we consider KD value based on the increased area?
No, for facade design, we have got a new code. You can do that way also. We have got now a new code from CED 57. We only have formulated that code. We means through number of discussions under the chairmanship of Professor Prem Krishna, there is a code for facade design. May I name the code? Or you can search it, facade design. Just a minute. I can give the code even.
Sir, if you can share it, it will be well and good, sir.
Oh, okay. Facade IS CED 57. Lot of discussions were there for 2 years or 3 years. Then this code came. Let me check. I am presenting probably like first. Which one is determination of randomness out of. This is the one for improving cyclonic resistance. This is the Tucker method of determination of performance rating with susceptible building. Yes, this is the code. So I present it with very small code, but it is again further being developed. First time it was published so quickly, it had to be published. In 2023, it was published. So I present. So yeah, I have to go to Zoom. Not this one. Yeah. Interesting. This code was developed after a lot of discussions.
Yeah.
Could you see the code now?
Sir, we can see the screen. There is a Google form which is popping up.
Okay.
I think it needs to be, the tab needs to be changed.
Yeah. This one, yes.
Okay, this is IS 17951.
Method for determination of performance relating to
the safety of external
building envelopes, also known as facades, impacted by wind-borne debris. So quickly, let us go through as you told. So the debris weights can be as high as from 1 kg to 4 kg, 50 kg, up to even more than that. Normally in Delhi, wherever there is a cyclone, debris has been very dangerous for the next building actually. So we had to consult these. There are so many STM codes and reports, and then these are the very simple. We define missile, which is missile, the object which is propelled towards a test specimen. How to test those facets? Some method has been given. Here you see fenestration assembly, the construction intended to be installed to fill. Okay. So just I'll project it quickly, page down करके, let us see what is there.
Sir, this is for testing, I think, sir. Whether for the wind load consideration also, we need to take this code, sir.
For local pressure coefficients are given in the IS 875 part 3.
Okay.
For facets. But for impact, you will get some idea whether how to take care of those impacts for the facades
Okay, sir. Okay, sir.
due to
Thank you.
debris.
Okay. Thank you. Thank you, Mr. Raghupati. There is a question from, sir, you can unshare the screen.
Okay,
Yeah.
just 1 minute. I like to
Okay.
see.
Okay. You wanted to show something? Okay.
No, see, just these are the tests how to do.
Okay. This is the details of that missile propulsion.
Test, device and test. Okay, unshare.
Okay. Yes. The next question is slightly lengthy. The question is related to the how to decide the geometrical scale and velocity scale, especially in the wind tunnel. So the question is, let's say there is a 100-meter building which is coming up in an urban area where the basic wind speed is up to 50 meters per second, and it is to be designed for wind loads. Now, the question is how the geometrical length scale and velocity scale is decided, especially for wind tunnel testing, by making sure that the scaled model results translate well to the prototype building.
Frankly speaking, I should refer this question to my seniors who had done experimental job. I didn't do experimental work, but
Yeah.
there are some theorems like Buckingham's pi theorem for modeling, like we do brick work, brick buildings and that masonry buildings subjected to earthquake. There we use Buckingham's pi theorem. Similarly, there are some scaling laws. If you go through Davenport's work or any published work, who
Right.
had modeled, a lot of guidelines are given in the Davenport's book or published papers. There are some books. I have not done this actually for further studies.
No problems. Okay, thank you. The same speaker is asking that, could you please share your insights about the history of peak 3-second gust that is being adopted in the Indian code? Your
Oh,
quick thought on it.
that's a story. My real life story I could listen from one professor of Australia who actually did this wind speed, this zoning, 3 mm or 10 mm, 10 meter or 10 minutes or 1 hour. What happened? They had a very hilly terrain in the southern, somewhere in Australia, southern part near New Zealand. So what happened? They initially their student used to go and take the data, but it was so difficult to approach during wind and the terrain also. You have to cross some rivers, then river, mountains, and go to the site. So they could not take the average of 10 minutes actually, 10 minutes interval, 1 hour they took, and they published the result in a wrong way, unknowingly by some mistake. And the whole world took that data and designed all many buildings after that. So he revealed about this mistake in Australian code and then adopted by other codes, and so many buildings were designed. And during Chennai conference of APCW 2014 or 13, he told this story. So 3-second, how it came, 3-second gust factor, after a lot of experimental wind tunnel study only this was decided. That 3-second will be a good time span to capture the peak wind speed, peak value.
Okay, sir. Thank you. Mr. Raghupati, there is one more question from your side. If you want to ask the speaker directly, you can.
Yes, sir. So actually, like long span flexible structures, tensile fabric structure, if we are using, what type of things we need to consider during the wind tunnel studies? Are any specific things we need to look into that? Because normally for the tall buildings or rigid structures, we may go with a generalistic way. Any specific things we need to look into that during the
Uh,
uh, wind tunnel studies?
as can be done, like some of the wind will be entrapped in uh, that type of structures. Like I have a umbrella. Why the umbrella goes away? Because the wind is entrapped and the whole mass is going to now flow away the umbrella. Similar to this type of tensions, the different structures. That additional thing is not only the pressure, but also that mass into velocity, that it would be increased pressure because of that entrapped air inside. So I think you can go through the works of Tridib Trideep of IIT Kanpur. He is recently publishing very good papers on these aspects, okay, of tensile defense structures.
Okay, sir. Thank you. Thank you very much.
Thank you. Thank you for your question. Sir, one of the participant is asking whatever changes you have mentioned between the two codes, are these changes are mainly for tall buildings or applicable to some other types of structures as well?
And low-rise building also it is applicable.
Okay.
Because interference factor can also occur for low-rise buildings. Say, for example, interference factor also for low-rise buildings also has to be taken. Even in coastal areas, the cyclone factor should be also taken for the connections or local pressure, wind pressures or connection design for low-rise structures also, industrial structures. So it's applicable for both types of building. Only the across wind loading part is for tall buildings. Along wind part also is for small buildings also can be. I mean, that part, gas effective factor fully on devoted for tall buildings. Otherwise, the revised code fast part is that is also known as peak wind approach part. Peak wind approach, 3 minutes, 3 seconds average is very peak, very high. That's why that value, that approach we call peak wind approach. The second gas factor we call mean wind approach. So for fast part is applicable for small low rise buildings as well.
Okay. Uh, Sir, the next question says when one should go for a wind tunnel testing. Is there any specific criteria or conditions when we need to go for such kind of testing in order to understand its behavior?
When the structure is abnormally unsymmetric, having reentrant corners or very tall, suppose I had seen one CSIR building in Kolkata. The land was very small, so they have taken the building just like this funnel,
Oh,
funnel.
funnel
Exactly,
type.
base may very small, but they have increased the everything like a funnel. So that type and very thin also. On the other side, it is very thin. Length is bit more. So that type of unusual buildings also where we change the symmetry along verticals like Colorado State University, some Colorado make building there is a building there also. So they change the geometry up. I have 5 or 6 squares. I discontinue one square after certain height. Then other corner discontinued. Then other corner. Then at certain height it becomes a plus. Only 5 fitness square. So about 5 square are remaining. Of 9 square, on plan suppose I have 9 tubes. So in the beginning 4 corner tubes are discontinued. So 5 will go up. Then after some time 6th tube is discontinued, 7th is discontinued, 8th is, and so on. The central tube will go even higher than that. So for that type of vertical irregularity, vertical discontinuity, we should go for internal testing. Also where H by A is less greater than 5. The
H
slenderness
by L,
H by base dimension.
base dimension. Okay.
Smaller base dimension, smaller of the two is greater than 5. We should go for we should be treating it as a tall building. It is given in the IS code only. I missed that. Could not explain probably. The slide is there.
Sir, one more question is from Mr. Raghupati only. He's asking which are the building can be considered as post-cyclonic important buildings apart from cyclone shelter, hospitals, schools and communication towers.
Water tanks, you can consider water tanks should be cyclone resistant. Some more structures might be there. Hospitals, so you have already told. Hospitals, water supply, fire stations. Fire station buildings are smaller height, of course.
Sir, do data centers will be on that criteria, sir? Data centers.
If yes, you can keep that also. Whatever be the, it depends on the client. If the client wants it.
Right.
Okay, sir. Thank you, sir.
So the next question is, I think we are finishing in just one, we'll take one more question. Could you please clarify whether IS 875 Part 3 includes guidance for external pressure coefficients, specifically for circular plan buildings with a diameter of approximately, let's say, 90 meters?
external pressure. Yes, there is a table 23. Table
Okay.
23. So there are different shapes of buildings, and depending upon shapes of the building, like chimney. Chimney is circular in shape. So there is a shape factor 0.7. You can reduce the load because it's circular. So streamline separations, etc., will be easier for us. It will not be that dangerous like sharp corners or blunt bodies. So there is a table where these shapes can be taken up, semicircular structures, fully circular structures, hexagonal structures. There is a table in 875 part 3. So you can apply accordingly. Different shapes. Would you like?
So
You can.
yes, yes.
I can show the table, but you just see the code
Yes.
from code.
So I just want to add a point, what Professor Mandal has already added when he has given that answer of Mr. Raghupati's question related to post-cyclone, what are the other type of structures? It may also include, let's say, some government command and relief centers. Especially, as sir has mentioned, that fire stations are one of them, then post-disaster relief command centers, some infrastructures and utility support as well. For example, power substations, power control rooms, even including the water treatment plants, sewage treatment plants, they have to be designed. And some warehouses, cold storage unit where the food and logistic safeties are concerned. And lastly, the community and the rehabilitation centers in general as well. I suppose these can be in some additional structures in addition to the what we have discussed.
Does railway stations can be considered in that criteria?
Should be
Right.
as much as we can. Okay.
So I think we have covered all the questions, sir, and thank you so much for patiently clarifying the doubts and the answers to all the questions which have been raised by the participants. So thank you once again for your time. Krishanshu, it's over to you.
Sir, thank you, sir. I believe the queries from all the participants has been addressed. Now, I would like to invite Mr. Gurkirat Singh Arora to deliver the vote of thanks.
Am I audible, sir?
Yeah.
Yes, you are. Please go ahead.
So, greeting to all. I am Gurkirat Singh Arora, a master's student at Earthquake Engineering Research Center. It's my honor and privilege to deliver the vote of thanks on behalf of the entire executive committee of IIT Shakti, IIT Hyderabad student chapter. First and foremost, I'll extend our deepest gratitude to our esteemed guest speaker, Professor Sasankasekhar Mandal, for his insightful presentation and enlightening session on silent changes in IS 875, Part 3, 2015, compared to its part in released in 1987 version, with recent research advances in across wind loading of tall structures. Today's webinar has highlighted the transition of IS 875-2015 now aligns Indian practices with international standard like Eurocode and ASCE. Refined gust factor method provide better precision of the background and energy ratios of the tall structure buildings. The code now includes critical updates of crosswind response and vibration analysis for complex structures. The CFD and the wind tunnel testing are now essential for the accurately evaluating interference effect between the neighboring buildings. Moving on, I would like to express our heartfelt gratitude to our faculty advisor, Dr. Praveen, for his continuous guidance and valuable suggestions throughout the planning and execution of this event. A special mention goes to the IT team for ensuring a seamless technical support and to the design team for their critical inputs and logistical assistance. I'll thank our program coordinator, Dr. Sunita Palliseri, for her continuous encouragement. I also want to express my appreciation to all the participants for their active involvement and throughout questions, which enhanced the discussion and made this webinar a collaborative learning experience. Lastly, I would like to acknowledge the hard work and dedication of the entire team whose collective effort has made this event a success. In conclusion, I extend my heartfelt thanks to each one of our participation and engagement. We extremely grateful and look forward to your continuous support in our future initiatives. Thank you so much.
Thank you. Thank you, Gurkirat. Thank you so much, Professor, for sparing your precious time and also for inviting our kind invitation. Thank you so much. And sir, if you allow, we would like to post this recording on the official YouTube channel of IAS Trucktee Student Chapter of IIIT Hyderabad, so that all the other participants who have missed this lecture or they want some more insights, they can again watch and gain the knowledge from your lecture.
Sure.
Yeah.
Can you send me also the
Sure,
link
sure. I'll definitely share the link with you, sir, once it
for
is done.
all other lectures also we can benefit
Yeah,
from.
sure, sure. Absolutely. Thank
Okay.
you. Thank you so
Thank you
much.
so much of you.
Namaste, sir. Okay. Bye.